All right, it's Friday. Got a 3-day weekend coming up, but let's do us some problems before we go on vacation. Or I guess you guys are probably already going to be on your weekend when you listen to this. But for me, I gotta do this before the weekend. So anyway, problem one, we got this snowball thrown at some speed. I think it was they said 14 meters per second, but whatever. And it gives an angle from the horizontal. It's at the top of this cliff. It starts with a height of h, whatever that was. Snowball has a mass of m. I think they said it was like 1.5 kilograms, which makes it a pretty dang huge snowball. And so it goes through the air, and then it goes splut. Okay, and probably kills a small dog. Anyway, so we want to answer a couple questions about it. So let's start with question one, which is how much work is done on the snowball by its weight during its flight to the ground below the cliff. Now, one way to look at that is to say, the weight on the snowball is going to be mg. That's the mass times gravity of the snowball. It's going to point downward, and the displacement vector is going to be delta r, and the displacement vector delta r is going to be some horizontal displacement it goes through. Let's call that d is how far it is between where we throw the snowball and where it lands on the cliff. So that's going to be d I hat minus, because I should probably specify coordinates here, right? So x that way, y that way. So positive x direction goes this way. That means this horizontal distance it goes is, or this horizontal displacement is d I hat. And then the vertical displacement goes down by h, so minus h j hat. You got that. You've got the force vector equal to negative mg j hat, right? Because it's mg and it's going down, so it's the negative y direction. Okay, so work done by the snowball's weight is just going to be force dotted with delta r, and that is going to equal negative mg j hat dotted with d I hat minus h j hat. Now we remember the rules of dot products. It's all the j hat components get multiplied together, and the I hat components get multiplied together, and those are 0. So there's no I hat component to the force. So really, the work is just going to end up equal mgh. So that is literally the work done on the snowball by its weight. Now, another way to look at it is to look at, we have this 1 and 2 here, right? This is our first state and our second state. So is to go at 1, we're going to calculate the kinetic energy, which is 1/2 mv naught squared. At 2, the kinetic energy, I guess you can say it's 1/2 mv final squared. So whatever. And then we want potential energy due to gravity at the beginning and at the end. Now, remember, we can pick any spot we want for our potential energy to be 0 at. So we could choose, normally we'd probably choose down here to be 0, and then we could say the potential energy at the beginning is mgh, at the end is mg0. But if we look at the problem, part C says if the gravitational potential energy is taken to be 0 at the height of the cliff, then blah blah blah. So in part C, we're going to need to use potential energy 0 at the cliff top anyway, right? So we're going to say U due to gravity is 0 here. So potential energy due to gravity at the top is 0, which means at the end, when it's gone down by h, potential energy is going to be negative mgh. So, and then you can calculate mechanical energy for both. But the real point of this is that work is the transfer of energy from one part of a system to another, or from one form to another, or from one body to another, or whatever. So we can think of our energy in the system as being in like 2 little buckets. Okay, so one bucket is our potential energy due to gravity. The other bucket is the snowball's kinetic energy. And if there are no non-conservative forces acting, nothing from outside the system coming in, so say we'll draw a little dotted line around this and say no energy comes in or out of this system, then all that happens is there's transfer from one bucket to another. And in this case, we start with 0 potential energy at the top of the cliff. we end with negative, which means we are, even though it starts with 0, we're still losing potential energy and gaining kinetic. It's being transferred from potential to kinetic, right? Because this decreases, which is this. If this is decreasing, then that energy must be going somewhere, and the only other place for it to go is into kinetic energy of the system. So I'm just refining my arrowhead here. So this must be the energy must be transferred into kinetic energy, and that is the work done by gravity. We say it's work done by gravity because it's energy being taken out of gravitational potential energy and put into the snowball's work. So gravity is doing work on this. Gravity is causing the energy of the snowball to increase, or the kinetic energy of the snowball to increase. Gravity is causing that to increase, and so that's work being done by gravity. So the work being done by gravity then is just mgh, which is what we got down here, conveniently enough. For part B, let's see, now it gets pretty easy. Part B, what is the change in gravitational potential energy of the snowball Earth system during the flight? Well, again, so there are two different ways to look at that. One is we just calculated it here, and we say change in U sub g is just going to be the final UG minus the initial UG, right? So negative mgh minus 0, and that's going to equal negative mgh. Okay, so that is our answer there for part B. Part B, right there. This is part A, right there. Another way to say it, you know, this change in potential energy. Well, the work done here was mgh, which means mgh energy got taken out of gravitational potential to go into kinetic. So the change in gravitational potential energy was the negative of this work that it did. Put another way, gravity does work, which means gravity is spending gravity's energy. Gravity is spending its potential energy. So if gravity spent this much energy, that means gravity lost this much energy. Just like if you spend, you know, $5 on a Justin Bieber CD or whatever you kids like to buy these days. I guess you're a little old for Justin Bieber, or whatever. Then you have $5 less, and then you say, "Wow, why did I spend money on a Justin Bieber CD?" And then part C is easy. If the gravitational potential energy is 0 at the height of the cliff, what is its value when the snowball reaches the ground? Well, we did that, so great. There we go. Negative mgh. It's right there. I won't go through the explanation because I think it's beyond redundant at this point, but let's just figure out what this number is. So it's mgh minus mgh are our two answers. And mgh, let me pull out the old power toy calculator, the mass of 1.5 kilograms, and that is a huge ass snowball. I don't care what anyone says. Okay, mass times 9.81 for g times the height of the cliff, which is 12.5. So my answer should be 183.9. So 183.9. And then the change in gravitational energy would be the negative of that, 183.9. And then the final, since we started at 0, the final would be negative 183.9. And let's just see, and yep, sure enough, those are all correct. Bada boom.